All right, it's my pleasure to welcome you to today's Center for Robotics and Biosystems seminar. I'm really pleased to welcome Russ Tedrake. Russ is the Toyota Professor of Electrical Engineering and Computer Science, Mechanical Engineering, and Aero Astro at MIT, as well in his spare time being Vice President of Toyota Research Institute. He's also a member of MIT's Vice President of Robotics Research, I should have said, at Toyota Research Institute. He's a member of MIT's Computer Science and Artificial Intelligence Lab, CSAIL. He received his bachelor's in computer engineering from the University of Michigan in 1999, Ph.D. in electrical engineering and computer science from MIT in 2004. He's currently the director of MIT CSAIL's Center for Robotics, and he was the leader of MIT's entry in the DARPA Robotics Challenge. So some of you remember that, getting humanoid robots to actually do something interesting. He's the recipient of the NSF CAREER Award, the MIT Jerome Saltzer Award for undergraduate teaching, the DARPA Young Faculty Award in mathematics, the 2012 Ruth and Joel Spira Teaching Award, and he was named a Microsoft Research New Faculty Fellow. His research has been recognized with numerous conference best paper awards, including in ICRA, RSS, Humanoids, Hybrid Systems, as well as the inaugural best paper award from the IEEE RAS Technical Committee on whole body control. All that aside, Russ does some really fascinating, rigorous, exciting whole stack robotic stuff. I'm looking forward to hearing about it. So please join me in welcoming him.
Yeah, great. So being a participant in the DARPA Robotics Challenge means I'm in the select few people that don't use a robot falling in the DARPA Challenge video. That seems to be the legacy of that challenge. Well, thanks for coming. I was originally scheduled to come in January, and then the snow came and I didn't get to come, so sorry. And thank you for coming in the second time. And I was reflecting this morning at how much has changed since January. Like the talk I would have given then is almost, out of date or something now. So originally we were talking, so let's just talk about diffusion policies, but the world is moving. So I would talk about sort of the foundation model version of that that's building on diffusion policies. So we're all in this race now. We're trying to see if we can bring ChatGPT type capabilities into the world of manipulation. And so Google's doing it and Facebook had it and there's some open source versions of it. I want to tell you a little bit about TRI's version of that today. I do think TRI is kind of an interesting entrant in this competition, if you will, this race, this enterprise. TRI is actually a pretty big organization. We have expertise across robotics, machine learning, and software. We have just enough resources to train some of the large models and also to do the empirical, rigorous evaluation that needs to be done, and to build the large, high-quality data sets, to work on hardware and software jointly. But we also have a charter of doing basic research, and sort of our mission statement says we're going to invent, improve new capabilities. Strong tradition of open source, and we have a lot of, I tried to call out a bunch of university partnerships and university funding. So everybody's claiming they have a foundation model. Everybody's trying to build foundation models. I think TRI is trying to sort our role in this, right? And I think I want to hear your feedback too about, I think if these things are invented sort of in behind a firewall, let's say, then that'll be a shame. So we're going to try to do things more open and try to tell you a lot of what's going on, what's working and what's not working. Just to give you the background and maybe to tell you why, give you the context of sort of why we think about this new capability slightly differently. The Dexterous manipulation is just one of the teams in the robotics organization at Toyota Research. The whole thing started in 2016, and we've been organizing ourselves around these challenge tasks. So one of the challenge tasks we did a few years ago was we tried to make a robot load the dishwasher. And this was sort of just after deep perception really started working. And so we'd have C1 throw a bunch of random things in the dishwasher. We'd have a deep perception stack, estimate the objects, segment the objects, do pose estimation on the objects. But then we had a very conventional model-based, well, it was a high-end model-based control pipeline to do motion planning. You know, we have a high-level task planner, and we could load the dishwasher fairly reliably. And we did a lot of work to make, to close the sim to real gap, have very good models of this. We did large-scale Monte Carlo testing to make sure if we made small changes in our big complicated pipeline, we would understand what happened. And we got that system to a pretty high level of reliability, despite the complexity of all those pieces. But then a couple of years ago, we said, we've invested so much in model-based everything, simulations, everything. What do you do when you don't have good models? Because there's a lot of things we want to manipulate where we don't have good models. And so we chose food preparation as sort of our next entry. And that's what really, that decision, I would say, is what took us down the path a few years ago, before it was so cool, to start leaning into imitation learning, right? Because roughly, if I'm trying to make a salad with a robot, then starting with a simulation seems like a tall order. Even if you can simulate a salad, to try to connect the perception of the salad into a state for your simulator seems like a hard task. Which means a lot of the RL pipelines that were starting to work well, but were based on simulation, were out. And anything that sort of immediately required estimating the state of the world in completeness was ruled out. So we started talking about, should we, you know, the different approaches we had available, and there's only a few really. I mean, you could try to learn a world model, you know, do a Sora thing, let's say, or you could lean into behavior cloning. So a handful of years ago, we started leaning into behavior cloning. And this actually started from work at MIT. This was Pete Florence, Lucas Manueli, Yunzu Lee, and others. That was my first taste of seeing what it looked like to do imitation learning for visual motor policies on a dexterous manipulator. So we were closing feedback loops through the camera, which I was very worried would be very fragile, but it could be surprisingly robust. And the type of feedback responses that you could get from these systems, it just gave a kind of, it felt different. It felt like it was a more robust system than what we had been building before. Pete and Lucas did all kinds of cool experiments that, for me, that was the moment where I was like, oh gosh, this stuff's really powerful. I have to think more about this, right? And the basic idea, of course, is just take a big, often pre-trained network and stick it through. It often was a relatively small policy network at the time, but the key idea in the middle here is that you're not explicitly estimating the state of the world. You're letting the learning system somehow come up with a learned state representation. I really had to stop and reflect on my core beliefs, right? So one thing that I immediately agreed with was that the value of using RGB, not just depth, but RGB at high control rate as a sensor was just undeniably powerful. The things we could see coming out of that cannot be ignored, right? I don't love imitation learning per se. I think decision-making is more than just copying, you know? But I did convince myself then that it was an awfully clever way to explore the space of policies, right? I want to know what the right policies should look like. So if I can play easily in a supervised learning setting, then maybe I can get the architecture right and then figure out how to design it with better tools. And again, the key is that we don't need a model of the world to do this, and we don't even need an explicit state representation. So we've been exploring, and then the thing that started working well, there was a lot of things that didn't work, I should say, that worked in a narrow sense, but really, I should have put it in. So Andy Zhang had a great slide for a number of years. I like Andy a lot. He had a great slide of saying, like, how do you make a rock star behavior cloning demo? And it says, like, first, collect the demonstrations the morning of the demo. You know, second, make sure only you give the demonstrations. Don't let anybody else touch your system. And these systems were working, and they were starting to produce good results, but they were very dependent on the quality of the demonstrations, and they were brittle. And so, you know, some of the new tools from generative AI have changed that, right? The higher capacity models, I think we just didn't know what we were missing by some of the higher capacity models, and putting a diffusion head on the end really changed the game for us. So there's a number of great tutorials on this. I linked one here, and I can send it to anybody afterwards if that's helpful. But many people know about diffusion. I'll just give the very light introduction. We want a process that's going to generate new, let's say in this example, new images that are similar to other images. How do you train a model like that? Well, you take all the images from your data set, all the images online, for instance, and you think of that as a distribution of natural images that you want to generate from. The way you make a diffusion model is you take those images and you slowly add noise to those images to the point where they get to be completely random images, right? And that's an easy operation to do. You can take any image and add noise. But the trick is you're generating data that's allowing a model to go the opposite direction, to go from a noisy image, a random noisy image, to move back down and denoise the image back into something that comes from the original distribution. There's a lot of rigorous math behind it, and there's some very simple tricks that people have learned, and these things are just highly effective for learning complicated distributions, or learning the gradient of the distribution. Okay, so how do you take that idea and apply it to a robot? So here's a simple example to sort of make the case. Okay, you've got to push the T into a location. In the diffusion policy setting, the thing we're diffusing is an end effector trajectory of the robot. We start with a random trajectory that would have been complete nonsense. You definitely don't want to send that to the robot. And then we denoise it to a coherent trajectory that is similar to the ones you've seen in the distribution. And that distribution is conditioned on the current images that you're seeing and potentially the task. So it's a lot like going into stable diffusion saying, give me a picture of a dog skiing on a roof. My kids asked that one the other day. And this is now, push the T to the T, and it will generate now a hypothetical trajectory for the end effector of the robot, which you can then execute.
So Russ,
Yes,
in that video with the dots flying in,
Yes.
where they're starting, is that the initial random guess of a trajectory?
That's the equivalent of the random image. And then you denoise it down to a coherent trajectory.
And so those colors on the dots correspond to where they are in the trajectory.
That's right. And as I'll say, it's actually important that we predict an entire trajectory. You could think if you're going to use this in a model predictive control kind of loop, all you need to do is predict the next action. You don't need a whole trajectory. But it turns out, empirically, it's very important to predict a trajectory. We predict 16 steps forward, we execute the first half, and then we throw it away and predict the next ones. And I'll give you a hypothesis for why that might be important in a few minutes. Please ask any questions, it's great. So there is an architecture that seems to be the formula for making these things work well. It is, so there are versions that are CNN based, convolutional neural network based. There are some that are transformer based. Like that part, the encoder is fairly flexible, but there's kind of a formula on the output. Once you go from your let's say latent representation down into the diffusion head, these UNet architectures are working extremely well. And I think you can answer questions about that if we like. Okay, but this is a standard formula pulled from the diffusion literature for how to do this denoising layer. And so once we got that right, a lot of tasks that I had sort of on my bucket list of things that robots should eventually do just got it scratched off pretty quick. I mean, in a narrow sense, right? You have to demonstrate this, but then I'd always said spreading peanut butter on toast was something that I wanted to see a robot do. And this is chocolate hummus apparently is a little better than were available in Cambridge or something, I don't know, but this is, a robot that was trained to like a particular page in the book. And if it was on the wrong side, it would flip the book pages one way. If it was on the other side, it would flip to the other page. Yeah, the other way.
Just a question, are you using the same policy for all the tasks, or are you training a new policy specific to
In this example, it's one task, it's one policy per task. We're going to talk about how you get beyond that. Yeah, that's a big question. Good question. Right, so you see a lot of things, we see a lot of things we like in this. So there's branching logic. Right, so sometimes it has to turn left, turn the pages left. Sometimes it has to turn them, forward and backward. It'll use its left hand or right hand, depending on what the task demands. They work for surprisingly long horizon problems. You can load the dishwasher roughly with these things, each trained as a single task. Okay, and there's if you're willing to give the demonstrations, 50 to 100, maybe 200 if it's a live demo, then we get pretty remarkable rollouts. I always try to find a couple that we're doing these often. We're training new skills all the time. So I always try to find a few that nobody have ever seen before and throw them in here. Here's one from the other day. So we actually have folks now that are robot teachers at TRI that are trying to, I mean, it's actually a creative thing to try to come up with something you can do with a bimanual robot that you've never done before. That's not in the data set already. So they were doing Ziploc bags and pouring fruit into bowls. It's a multi-step, pretty complicated thing. And to be clear, this fails also. I'm showing a success in this video. I'll show you some failures other times. This is a capability that is sort of a raw capability. I'd say it succeeds more often than I would expect. It does remarkable things, but it's not close to 199%. I'd say, probably for a task like this, it's 70% success rate or something like this.
Russ, what about the speed which you can do it? Can you roll that out at a higher rate?
Yeah, so we've seen, so I think there's a couple of questions about that. Of course, one is just how good is your teleop setup? What can the demonstrations give? And then there's inference speed, and there's a couple delays that you could try to get out of the system. I think we're bottlenecked primarily by the denoising diffusion layer being just inefficient, not optimized yet. We know how to make that faster. We've seen people make that faster, but that's what's limiting our speed right now. But I don't think, I mean, the bigger models, you start getting maybe real questions, but I think right now there's lots of headroom to improve the speed.
So in this example, a teleoperator solved the problem 100 or 200 times or something, and there are cameras set up around here that are watching, and you're getting joint angles from the
Yep,
robots.
the input to the policy is all of the cameras. There's actually a lot of cameras. There's multiple, you can see a camera here, you can see a camera here, and both sides of the hands actually have cameras unless they get in the way of the task. So we have double wrist cameras. And then joint angles and velocities from the robot. In this case, that was the input to the policy.
Okay, so the teleoperator does this 100, 200 times or something, and then what we saw here was fill a bag with fruit, put it down, go.
Yep. And the mental model I have is that it's not magic, but in terms of kind of interpolating within the convex hull of the demonstrations, it does shockingly well. If you give it something, if you put a completely different Ziploc bag in there, if it works, you got lucky. Right? This is more about having very strong, generalization between in the interpolation sense, not in the extrapolation sense. The charter, though, is to build a big enough data set. The LLMs, where basically everything's
Everything's an
interpolation.
interpolation.
Right? That's the mission. Here's another fun one from the other day, right? So we were worried about whether thin wires, using RGB feedback only to sort of do narrow, thin wires and everything like this would work. It's shockingly good. And we have pretty much anything we can teleop, you can play back. There's some things that are combinatorially hard, right? That if it's not going to do well at it, like playing Scrabble or something probably would not be a good choice. But anything that's about the motion of the robot arms, it's very hard to find something that this can't mimic.
Have you tried with just a single sensing perspective, like from the robot itself?
That's a great question. So I really like the teleop setup you guys have downstairs, and Ed was showing me that. So right now, the human is watching from the side when they're giving the teleop. And if you did have a limited sensing for the robot, then I think it would be very important for the human to understand that limited sensing, to only experience the sensors of the robot. Otherwise, the human will take actions that the robot couldn't possibly mimic, right? Just out of observability considerations. In this case, we're trying to just, get around observability as much as possible in a sensor-rich kind of sense. Yeah.
Is your training process robust to the lightning condition because you use camera?
I think that I'd say we are a little robust now just because of the pre-trained representations and the visual backbones. And I think we would need to be a lot more robust but I think the computer vision world, I think, knows how to do that. I think we just need more data in that sense or different pre-trained backbones. So that one, I think the answer is no, but I don't fear that one. There's other things I fear. Yeah.
How often does the human demonstrator fail at the task?
Yep.
This is an idea of test difficulty.
Good question. So how often does the human demonstrator fail? So we give very few instructions to the demonstrator, but one thing we do say is when you fail, keep going, because that's actually the best demonstrations. We want to see the recoveries. So we don't explicitly encourage them to fail, but that's the best part of the data. And actually failing, I mean, sometimes I think the better demonstrators think about all the ways that the robot might fail and try to give examples of failing in that way and recovering. And that's what, so when we do try to make, so if we, let's say we give 100 demonstrations and we roll it out and we see it failing a different way. I mean, of course, there's like an active learning thing we could be doing very well, but training a diffusion policy takes multiple hours on the GPU. Typically we do it overnight. So right now we tend to do it in just like 2 batches. We'll say, oh, maybe give us a couple like demonstrations of these things we saw fail, throw them back into the data set, retrain, and then we've got something pretty good. I've never seen us go more than 2.
Sorry.
Yes, please.
Quick follow-up. So is it possible to train with multiple perspectives and then execute with just the single perspective? Is that?
That depends on the architecture of your coders and everything like this. I think like the Octo work was very specifically about trying to train with different mixtures of sensors and different mixtures of actuators so that you could be cross embodiment. And the core middle layers, sort of the representation learning was shared, and that does seem to work. It does need to be trained in that capacity. So yeah, why diffusion? I think we'll talk about a couple of the other options that are out there, right? One thing is I think we just needed a high capacity model and one that's just trains very reliably, right? We get away with a small number of demonstrations. It works on multimodal demonstrations. I think this was one of the biggest things for how it went from only a few of us a few of the experts could give demonstrations to anybody could give demonstrations. And this is what diffusion does well, right? I think so. One of the reasons we chose that T task was because it has an obvious symmetry. Demonstrators tended to, you could find yourself in a situation where you have to push the T this way and your fingers over here, that you could have 50% chance of going left, 50% chance of going right. This is just one of the simpler examples of multimodality. And I think some of our network architectures already did that very well, right? So like AlphaGo is clearly dealing with multimodality, but that's because it's a categorical distribution, discrete distribution of the action space. And we've always been very good at learning distributions over discrete. And what diffusion has added into the language is doing nice distributions over continuous actions, especially high dimensional continuous actions. So training stability and consistency. We just don't tune hyperparameters until we're really changing the architecture. We've got that locked in. Every new skill, we train the same parameters for the same number of epochs, and we grab the model and we're good. Yeah, this continuous outputs, I think, for me, makes a big difference, right? Compared to the categorical distribution. So RT1, RT2, these are doing discrete tokenization of the actions. And that can work, But I do think there's something, my controls bias maybe biases me towards continuous outputs. The action chunking transformers from Chelsea are continuous outputs. And I think those can work very well. I think probably the diffusion handles the multimodality a little bit better, but it pays a higher price in terms of inference speed. But I've seen both of those be very successful. I like that diffusion models have a solid mathematical foundation. Like you can think about what these are doing and just ask, if I ask it to demonstrate an LQR controller or an LQG controller, but does it do the right thing? And it does, right? Whereas you can't do that if the output is a discretized transformer of there's no like boiling it down to the simple case in the other models. We had a conversation about, should diffusion policies work for dexterous hands? And I think there's no question at this point that they do. There's lots of groups that are doing it. There's 2 I grabbed. One was from Karen Liu's lab. One's from Jitendra just the other day. I won't call out any of the specific companies, but some of the humanoid demos that you're seeing that are doing the dexterous hand demonstrations, the ones I know about are, many of them are using either ACT or diffusion policy. Okay, so that's built on a pile of robotics tools, right? One of them is haptics, right? We do have a very limited compared to what you guys are building setup with this haption. So we're just feeling the end effector forces as estimated by the joint torque sensing in the Francos. And in this case, this is one of the tasks where it made a big difference because of that kinematic constraint, right? The human operator couldn't feel the forces, then it was very hard to sort of like spin the crank and match that kinematic constraint nicely. But if you give them the ability to feel forces, it works pretty well. Now notice we are not looking through the eyes of the robot here. We're looking from the side here, and I think that is a limitation. We do have, model-based controllers providing somehow the safety cases. So the robot sends end effector commands, and then we push that through differential IK, operations-based control, depending on the variant. Okay, and we enforce the things we know about the world, like there's a table there. We want to make sure that and self collisions, those are all enforced with our low-level model-based control, and that has to be good. And we worked a lot about getting latency out of this pipeline, part of the pipeline too, and good system ID of the Francos. I think that makes a big difference. I heard somebody once say that he believes us that we've done this well because there's no scuff marks on the pandas. And then we have some amount of visual tactile sensing. So some of the demos I show will have a bubble inside it, and that's our version of a visual tactile sensor. They're big in the form factor, but they do make nice, beautiful contact patches and give good information, which can be sent back into the policy. Okay, but that's all about single task. There really are limits to what you can do with single task policies and the robustness is in fact to see. And so we've been scaling up. And so I think this is the kind of big question, big trend, if you will, right? So we've had large language models, then we had we're still building visually conditioned language models, VLMs, and the new popular thing is to work on these large behavior models. That's what we call them, or visual language models, or sorry, visual language action models, body foundation models. There's a couple different names they go by. And I think there's a big question there. Is predicting actions somehow fundamentally different than predicting next tokens in a language model? This is just, I think, one of the big questions that gets asked a lot. And there's a lot of reasons why you could argue that should be different. I think continuous actions, high dimensional, right? The feedback loop that's there has to obey physics and deal with the randomness of the real world. You have feedback and stability issues. Technically, a language model, an autoregressive model for language could go unstable, but it's got a bounded domain, so it's not going to go to infinity, right? But I would say that the success that we've seen now in single task behavior cloning, to me, says that these are not fundamental problems. I think the architectures we have been exploring suggest that we can predict next actions and see similar, I don't know about the scaling laws from that, but in terms of the ability to see generalization and this sort of basic architecture, I no longer think it's dramatically different than predicting next token in an action. Except in a couple subtle ways, maybe short-term ways. One of them is that we don't yet have internet scale action data. We need to come up with that somehow. And another one, and this is, I think, surmountable, but so far it's a real problem in the field, is that we don't have rigorous and scalable eval. That's what the machine learning folks would call it, the eval pipelines, right? Benchmarking, if you will, right? If I want to change my architecture, change my data slice, does that make the model work better or not? You need a very solid pipeline for that, and it's hard in robots. So let's dig in a little bit, yeah? So the way we're thinking about it now is that you need a data diet for your robot, okay? So we have robot teleop. We're investing in getting a lot of that. And I consider that very high quality, precious data. At the other extreme, you have internet scale data that's already being used for video prediction models or just language models, everything in between. And this is the really big data, okay? But there's also a big transfer because, you know, it's not a lot of videos of pandas manipulating, you know, that gray mat online, right? And it doesn't have action labels in it, but it seems like it should be relevant. And on the robot side, we have no transfer, but we have small data. And the important thing is that there's a lot of things in between. So when you think about the OpenX embodiment data set by Google, this is a cross embodiment data set, lots of different robots inside there. And doing lots of different tasks. Some of them I care about, some of them maybe I don't. So is that useful? Well, I'm gonna have to transfer from those other robot embodiments, different camera locations or whatever, to mine. So it's a little bit along that axis, but it's at least robot data and it's got action labels. So in that sense, it's sort of closer to the small data. We're building, of course, simulation tools also for data generation, right? And those, I think, the discussion about sim to real and making that gap as small as possible, my thinking about it has changed a little bit. It doesn't have to be perfect. It needs to be big in data, and the smaller the sim to real gap, the smaller the transfer is. But we know more and more about how to do this transfer learning. So it actually doesn't have to be perfect simulation in order to be useful. And then there's a bunch of other things in between. So there's novel teleop devices that are coming out. There's data sets that people are, let's say, labeling video data sets with human annotations of, like, you know, skeletons or hand tracking. There's all kinds of things in between. And so I think one of the new missions is to figure out in this time of small robot data, there's going to be a time in the future where we have big robot data, right? But we just have to get off the ground and make robots useful enough that there's a lot of them out there. Then we have to figure out how to sort of use both sets of data. And the reason that could make sense, I think, how could you possibly take data that's not action labeled and use that for predicting actions? Is because I want to start thinking about action prediction as representation learning, okay? So, and here's where it's a simple analogy here, but both the ACT line of work from Chelsea and the diffusion policy line of work, they're predicting sequences of actions. And empirically, you know, Chung and Tony both say, like, this is super important. Don't really understand why, but it makes a huge difference empirically to predict actions. And here's a simple thought experiment. And I don't know, this is just one hypothesis for why it could be important. But imagine you had a linear dynamical system, back to familiar territory for me, right? I'm just got a demonstrator that's a linear policy. And I just want to mimic that, okay? If you want to predict future actions, of course, if you're just predicting one-step action, the learning system just has to learn negative k, right? Because if you're giving state observations, it just has to learn negative k. If you're going to predict future actions, then what does the learning system has to learn? It has to learn a minus bk to the nth power, you know, and then k. And so, okay, that's just a simple thing, but it makes the point that if you want to be able to predict what the actor did in the future, you implicitly have to learn something about the way the dynamics evolve, right? In order to be able to, like, if it's a state-based policy, you have to know what the state would have been so that you can know what the state-based policy would have done. And you don't have to learn all of it. You just have to learn the task relevant one. If K, for instance, I mean, this is where the linear analogy only goes so far. I mean, K would have to be all zeros in some axes, but basically, you know, if the policy didn't use all of the states, then you don't have to learn about those. In a nonlinear setting, it's much richer than that. But so why could I use, you know, if there's a robot opening doors in the RTX data set, let's say, and maybe they don't even open the doors the way I would want. It's kind of a clumsy opening the door. That's still valuable to me, because if I watch that robot predict the opening doors and I can predict its future actions, even if I throw out the policy part, it at least told me to focus on the features of the door handle and, like, you know, the Kleenex box in the corner and all the other things going on in the room were not essential to accomplishing that task. So in some sense, action labeled data is an incredibly powerful way to tell me about task relevant dynamics in the world. Okay, and now if you don't have action data, predicting future images is a more expensive, less, that's trying to get everything about the dynamics. But this is where I think they're both trying to learn fundamental things about the world and asking them to share a representation so that they can both do their jobs allows you to transfer some of the capabilities from video prediction down into the action space. And okay, so we're scaling up. We have lots of robot demonstrations, lots of data. We have this, we're calling the CAM data set because it's in Cambridge, where we've got that bimanual robot doing pretty much everything we could think to bring in front of a bimanual Panda. This is numbers of skills just going up and up. This is what the Cambridge TRI lab looks like. It's just a block down the street from MIT. There's lots of Pandas doing lots of things all day long. We collaborated with Chelsea and Sergey on the droid data set. TRI contributed a lot of the data into that actually. And this was more about diversity of the environment, where the CAM data set is limited in environment diversity, but task diversity is very rich. This was trying to take robots out into Airbnbs, for instance, or things like this, and try to do, you get task, even if you do simpler tasks like opening doors, refrigerator doors, because every refrigerator is different, you get a different type of diversity. So those are a couple entries on the data diet. That's kind of in this side. Let's move a little to the left. We've been continuing to collaborate with Chung and Sharon. They're fantastic. And working on these universal manipulation interfaces, one of the simple interfaces. And this is Chung showing it off. So now humans can just grab this. You don't have to have a robot to get your teleop data. He's just got a GoPro, is the only onboard sensor. It's recording into MP4 and the IMU in the GoPro. And every bit of data you need, even for bimanual tasks, because you can reconstruct and figure out what the hands were relative to each other through some SLAM kind of inference. You can use this to transfer it to a robot and then potentially dramatically scale up your robot data collect.
Is there any force sensor on the grippers?
No, no force sensing there. I remember Chung asked me if yours and the grippers were waterproof. I was like, no, they're not waterproof. Then he sent me this video. I was like, what? But he's awesome. He's got it working. Okay, so that's like maybe moving that way on the axis, right? TRI's got a pretty big effort in to do VLMs. We've done some of it in collaboration with Dorsa. So we have sort of state-of-the-art open source visual conditioned language models. There's a Prismatics VLM project that's already been pushed out. And we're trying to use those to make open source reproductions of like the RT2 style visual language action models. We're working on video diffusion, I think Sora, right? Team at an ML team at TRI that's working on diffusion-based video prediction.
Sorry, can you go back?
Yeah.
So just straight video prediction?
There's a separate project that has been going on in straight up video prediction.
So no robots involved?
No robots involved in that. Now, the teams are aligning and trying to figure out what happens. Yeah, how do we take those representations and use them to make stronger robot policies? Yeah. And you can see there's an intermediate point where you start having videos of robots, for instance, from our CAM data set. And all of that is kind of just phase one, right? So this is just to get the robots off the ground, to make them kind of useful, right? Hopefully enough to, I don't think, a lot of the ways that people are using robots in industry today, this would not be a great match for, right? If you need 99% success rate or 99.9999% success rate, that's not what these are good at yet, right? What we're building is a very general, kind of sloppy capability, right? And I think we need to figure out how to use that, because that is useful. I mean, people go through this learning curve with GPT too, right? The first time I started asking questions, like, it's gonna give me the answer to any question. Well, no, it's gonna get it wrong a lot of the times. Okay, but that's still useful. You just have to learn how to use that. And I want the same thing for, I mean, there is a beautiful analogy, I think, to the LLMs, right? I can ask GPT anything. It might make something up, but it always generates beautiful prose, right? I want that for my robots, right? I want to type in, make me a pizza with this, whatever. It might not make a great pizza, but I always want it to take reasonable actions. If we get that level of capability, that will be something new that we don't have before. And I think we need to get that and embrace that and study that and understand what the heck that can be good for. And then I think we can start going vertical, because when you do try to go into to get 99.9% success rate with something, then having this capability, which has seen a little bit of everything, you can bring into that vertical a wealth of like recovery strategies and coping mechanisms so that when things do go wrong, you have all those at your disposal. So that's the mission. And then, of course, there's more and more ML ops, machine learning operations kind of stuff to deal with once you get to really large scale data. Even that, I kind of think of behavior cloning as only the first phase, right? I mean, really, if you think about how AlphaGo did it, behavior cloning was just phase one. They got to good players, but not championship level players. And people say this for LLMs too. Even the most enthusiastic LLM folks say, well, it's a little disappointing that it can never generate new knowledge. Right? There's more to do, right? And I think robots are going to need that too. And I actually asked before giving the talk, should I talk about the math stuff and graph of convex sets, or should I talk about the learning stuff? And the vote was for the learning stuff, but a little plug. We're working hard on the math too and the model-based control, and we have some of the best model-based control we've ever had in this graph of convex sets line of work. And I think I'm trying to bring these two worlds together. I'm trying to say that this is going to help us sort of fill in the gaps and do planning, even if you bring your large behavior model back in. Okay, last idea. I know I would ask to keep around 45 so we have discussions, or
Yeah, I'm sure there'll be a lot of Q&A, but keep going.
okay. The other side of this, I said, is that predicting actions is different. And it's because we need rigorous, scalable eval. So here's just an example, right? So we asked the robot to make a salad. It came out like this, right? And you ask 3 people, you know, is that a success? Is that a failure? You're gonna get 3 different answers, right? I mean, there's only 2 choices, but someone gives a 0.5 or something, right? And of course, if it was the person who gave the demonstrations, they're the one that's gonna call it a yes, right? So Hadass has been visiting, Hadass Kreskis has been visiting TRI on her sabbatical this year and has really been hammering on us with this. Like, we're just need to be better about doing rigorous empirical science in these pipelines. And we've been getting a lot better. So simple thing that we all know we should do, but one you must do, and the field isn't doing it enough, I think. You have to do rigorous evaluations, including blind randomized testing, right? When you're asked if you're going to do hardware evaluations, the person doing the test cannot know which policy is running, and it changes on every rollout, right? Otherwise, it's biased, and you need to get bigger numbers than we're typically reporting in papers right now. Of course, in hardware, you can never run the same experiment twice. So the dream is to do a lot of simulation testing and slowly close the gap between not the specific rollouts, but what I want is that the total ordering of performance of policies in simulation is predictive of the total ordering of policies in real. So this is a Drake simulation that's just one of many that we've been hammering on. And behind the scenes in Drake is these good contact models that I think keep the sim to real gap a little bit smaller. Just to put a plug in. So the philosophy we were saying, so I was talking earlier to a few folks. I think there's maybe 3 of the most mainstream simulators out there in robotics right now: Mojoko and PhysX and the Isaac Sim world, and Drake is probably the distant third, I know, but it's there. It's being strong, and there's a philosophy in Drake of being a little bit closer to real-time rate instead of super high speed, but being very accurate. So this is, I just, a detailed contact model of the hand interacting with the mug, where we're doing computation to compute contact surfaces and taking nice smooth integrals. But even when you see papers like this that we're actively writing papers on better simulation, right? We're always doing things to like compare the ground truth, if there's a known solution for that, that we're making sure our solver gets this, there's like a level of rigor that we're putting in that I think distinguishes. It's just not, we're not as much about speed, we're more about closing the gap. And so there's a role for that. It might not be the right simulator for you, but there's some tasks where it's very good. And we have deformable FEM models that have rigorous thinking about frictional contact between the deformable and rigid. We have NPM that's coming soon. This is a paper recently, but it's not in main Drake yet. But look at the rolling pin spinning, right? That's a frictional contact interaction between a granular media and the particle simulation. And again, you'll see the material point method work. It says, okay, if I took a bunch of particles and simulated a sphere rolling down an inclined plane with that, do we get the right answer? We always try to compare in that way. NVIDIA is saying that they're going to help us make this better. So I think that's a kind of a stamp of approval, and they see it as a way to include Drake in the Omniverse eventually, and bring some of the higher fidelity physics into the pipeline. Okay, so we are trying to build a foundation model for manipulation, right? Why? Not because it's cool. Well, it is cool. But I think we have to start the data flywheel for general purpose robots. And for me, this is the big one. I do think that the way we have to think about control is changing. And there are some pieces of this that you can only study when you get to the bigger models. And I don't want to read about that on a blog post. I'm just going to suffer the early adopter pains and try to be on the front lines and try to really understand how this makes me have to think differently about control. And I really want to emphasize, I know I showed a lot of things working and it looks cool, but there's so much work to be done. There's so much we don't understand. I feel if I had given the other talk, the graph of convex sets talk, then I would have had an answer to any question you would have asked, almost. Maybe you had a real good one. But in this one, I feel like we barely understand what's happening, right? It's working empirically so well, but I mean, I can tell you some of the hard questions. And I think we must bring our understanding of dynamics and control and haptics and everything into this world and build a stronger foundation underneath this. Yes, some of these really do require scale. That's one example I could talk about if necessary. It's a great team at TRI that's been making this work. And we are hiring a little, so good. Yeah, take any questions.
Great, thanks, Russ. We have time for some questions.
So I can post a blog online. I can take a video in my backyard and upload it to YouTube. But if I am a hobby roboticist and I want to contribute to the robotic data set, how can I do that without access to vast resources?
So training the big models is expensive. Makes me sick. How much money goes into some of these things. But I think fine tuning. I mean, there's ways just where I think it is approachable to work with these models. I think you need access to the big model to start from. But I think there's a lot of things that can be done on a couple of GPUs, in your lab. So I think some of the science questions and certainly making robots work better can be done without the massive compute. I think there's probably going to be a world where, so a lot of people, for instance, if you're going to build a new vision model, they're going to, a couple of years ago, it was always ImageNet. You'd start with a pre-trained ImageNet model, and then you did a little bit of fine tuning, and now you had a pretty good mug detector for if you're building dishes out of the sink. And I didn't have to retrain ImageNet, right? I just had to train my mug detector. And I think right now, as soon as people start releasing the bigger open action models, you'll be able to grab those and fine tune them on small data sets and see good results in your lab beyond the zero shot sort of performance. That's approachable. There's a harder question there, which is like, yeah, how do you get your hands on the really big things? And I think probably some of these really hard questions have to be articulated in a way. I think there are things that you can solve on a chalkboard once we really can articulate the core challenges. And I think everybody should be participating in that. There are a few pieces of this that I do think just takes a lot of money right now to nick out to get us to the next round. Malcolm, how's it going?
Great, good to see you. This issue of like how you tame the exponential growth of sequences when you're predicting over sequences or actions or language or Go, the alpha star approaches, you marry MCTS to neural nets at key points of the network. And I'm curious whether that is helpful here, and super curious about what sort of stuff you're doing in MCTS. I sort of wish that talk had been given because it's such a crucial issue.
Yep.
How we tame the computational complexity of sequences, and super interesting to me that the brain figured this out with motor cortex when we came up onto land because we had kinematic chains to control. And we didn't do it in water because there was no such chains to control. And it's really sequencing of action that preceded language. But
It's strange how the language models came up first.
it's exactly the reverse. So, but anyway, I'm curious whether that approach is useful, sort of hybridizing MCTS with neural nets at key.
So maybe I'll use, I had my sort of backup slide before my final slide on this, but so I think this speaks to it. So one of the things that we kind of know about imitation learning, and what you're speaking to, is that you want your rollouts to be stable, stabilizing, right? So because otherwise, if you have a bunch of data, this is the dagger story. Drew Bagnell made beautiful examples back in the day of let's say you learn to drive a car on the road, and then if your policy is just a little bit wrong, you go a little bit to the side of the road, and then you don't have any data, and then you go way off the road, right? So if you don't have something stabilizing, then you can get in trouble fast. But I also said that multimodality was important, right? So you want to be able to go left or right around an obstacle or left or right around a T. And those seem like they should be at odds, okay? They're not strictly at odds. It depends on what kind of generalization you have. So, and this is one of the places where we are trying to understand and shape the way these models generalize. So for instance, if you were to take a bunch of trajectories that were, let's say, starting over here, maybe all the trajectories go left around, and you want to somehow transition to the trajectories where all of them go right around. And I've got a distribution that looks like kind of on the left side, there's a distribution on the right side. How do I interpolate between them? If you Wasserstein interpolate, and that's sad, you're going to go right up the middle, right? If you total variation interpolate, where you kind of go like this, that's good. There's other cases you can come up where you kind of want a Wasserstein interpolate. Okay, so there's a lot of questions like that we're trying to dig into and understand. But the stability that we're talking about here, maybe to actually answer your question, is that I think we're getting that in these manipulation tasks, both from our low-level controller, which is simple model-based controller, and from the physics of the world in these settings being relatively plastic and dissipative, right? And I think these tasks are not quite open loop stable, but almost open loop stable. And I think we're exploiting that. We've seen people do more dynamic things, but in the setting that I've studied most closely, I think we're getting a lot of stability in the rollouts from choosing tasks that are, and maybe most of the tasks we want robots to manipulate are this way.
Oh, that's really interesting. So we could see sort of like with LLMs, you're seeing sort of use of childlike word sets before progressing to full adult word sets as being a very useful approach to getting small LLMs that are hyper efficient. I wonder if you could do the same thing with really stable.
We're kind of building a kindergarten
Yeah,
set up
exactly.
here.
That's super
I'm not
cool.
against that, yeah,
Thanks.
sure, yeah.
I really like the perspective that you shared when you did the little linear systems analysis to sort of like convince me, and you succeeded at convincing me that action sequences in some way encode something about the underlying dynamics. I think that there's some truth to that. And so I guess what that means is that if you're in the business of predicting action sequences, then whatever demonstration you receive are specific to the embodiment of the system that you have right then and there. So I guess that gives me a system-specific understanding for how this works. And I guess the game for LBMs would be to, just have a lot of those sequences and hope that you get some nice interpolating capabilities. But, just now as you were mentioning like highly dynamic tasks, do you believe that we're gonna be able to see generalization to these kinds of like more complex dynamic systems where you can have a lot more expressive dynamics like straight out of these action sequence type models?
Good. So I think, are we learning system-specific dynamics? I think that's an interesting one. I have no math to support this, and I only wild faith and belief or something. I mean, based on things I've seen now, right? I think when you start training data cut from multiple systems, it seems that you're able to transfer some of your understanding from one domain into the other domain. Think of it as I have to pick a Z, a latent vector Z, that is sufficient to predict the dynamics for Francas and for Kukas or something like this. And at some point, if you do that with enough different tasks, then I think like language models, maybe we get to the point where it's learning something more fundamental about the physics of the world in that representation and a little bit less robot specific. So that's to the one point. The dynamic tasks, I don't think I think that's kind of like I forget which example I used, but if you're not in the convex hull, I don't think you just imagine, like if you've never seen a data of robots doing backflips, I would not expect a robot to successfully do a backflip. I don't know if you can teleop a backflip, but that starts coming in the data set. I don't see, as much as I care about those systems and the richness of them, I don't see that it's fundamentally different from the learner's perspective. I think generalization in that space should look similar to the generalization we're already seeing. And we have seen people doing diffusion policy on dynamic things now. Sorry, let me go over here.
Dr. Tedrake,
Oh, yeah.
we have an online question. Could we do that really quick?
Yes.
So the question is, it's about generalization. If you change the number of clothespins, or if the number of clothespins you use depends on the size of an object, can it do something like that?
Yeah, that's a great question. So the clothespins specifically, I think might have been trained with just two. There was one happening actually the next station over that was specifically targeting this question. So it had to put cans into a beer cooler. And this was all about the number and the sort of minimal combinatorics of the task could change, and it showed generalization across that. So if you only train with two clothespins ever, then if you ask it to do three, I wouldn't expect it to have its repertoire. It wouldn't be able to do that immediately. But if you've trained with a mixture of different numbers of objects within some limit, again, it's not going to solve Go, but there is some generalization there that we're seeing. Yeah.
You mentioned there's some mathematical significance to predicting, not necessarily like the next immediate step, but like a bunch of steps, and then like there's also like maybe a heuristic or like a reason for discarding half of that and then predicting like a new. Could you elaborate on that a little bit?
Empirically, we see that this is very helpful. Okay, we've done lots of slices of how much to predict or whatever, and I think that the question of why is it 1.6 seconds is probably about the time constant of the tasks we're picking, not something fundamental in learning theory. The statement about the LQR kind of analogy says that it's putting different pressure on my representation to try to, you have to learn something about the dynamics in order to predict future observations. The other piece that we're throwing in here is that if we're doing it in a feedback loop, so we have a model predictive control kind of thing where we're going to plan for a little bit, execute for a little bit, plan for a little bit. Empirically, we're pretty happy with 0.8 seconds, and then we plan for 1.6, we execute for 0.8, but that's for a whole bunch of like systems reasons. How fast do we diffuse our models? Like how fast do our cameras update? Things like that. So I don't know if I don't have a fundamental mathematical reason for why 0.8. I think probably the shorter window of execution before you use your feedback, the better, I would think. Our history of observations is actually relatively short. For some other subtle reasons too. I would like that to be much longer. But at some point it does become, like mixed up with the math gets mixed up with the systems implementation. Yeah.
I think we'll make this the last question, just so the students have time to have lunch with the speaker, so go ahead.
So you mentioned that it's important to collect recovery data from like a near failure, challenging instances. How about complete failure? Can we get use of like negative data where we don't want the robot to behave that way? Both from teleoperation perspective and also, for example, for a 70% success rate, can we use the other 30% to train again to further improve the performance?
It's a great question. Yeah, so I remember there was a day where someone at TRI told me that they had thrown out some of the data or whatever from the teleop, and I was like, come on, I thought the philosophy was that all data is good data, including the recovery. He said, we slammed the camera into the table and it fell off. We don't want that in our data set. Okay, that's a case where I would admit that we don't want that in our data set. So I have seen this, but I don't have a principle. I think right now we're just manually saying, in a very rare case, if that happens, take that out of your data set. There's a much smarter thing of trying to use counterexamples and somehow putting pressure on there so it doesn't happen, which we're not doing yet. But it's a great question.
Okay, let's please join me in thanking the speaker.